Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are going to talk about multi-modal large language model applications. This episode is based on a tech blog titled Scaling Catalog Attribute Extraction with Multi-Modal LLMs, written by the Instacart engineering team. You can find the link in this episode description. Throughout this episode, we will explore this topic from both the business and data science angles. Now, let's dive in. Instacart is a leading grocery technology company in North America. It partners with thousands of retail partners and delivering from more than 100,000 stores. Their mission is to make grocery shopping seamless, whether the customers order online or browsing through their apps. To power features like search filters, dietary badges, and recommendation engines, Instacart needs highly accurate, structured attribute data. Attributes include whether an item is organic, its flavor, its size, or even something like sheet count for paper goods. Think about it from a shopper's experience. When you filter for organic strawberries or look for gluten-free bread, you expect the right item to appear instantly. Behind the scenes, that requires the company to correctly tag every product with detailed attributes. If an attribute is missing or wrong, the user experience breaks. Shoppers might see irrelevant results or miss out on items they wanted. With millions of products constantly changing in their website, keeping this catalog accurate is no small feat. Now that we've understood the business problem to solve, let's dive into the technical side to see how Instacart tackled this challenge. Let's start with some traditional approaches Instacart used before moving into large language model-based applications. The first solution was SQL-based rules. Herein, SQL stands for Structured Query Language. Essentially, these rules rely on SQL queries combined with some regular expressions or string matching operations, and it can systematically extract attributes from the text of the product description. For example, if the product description contains the word organic, a rule can be defined and used to tag this product as organic. While this approach is simple and relatively scalable, it could break down in messy real-world cases. A product description that says flavored with orange and mango might confuse the system. Should this flavor be orange, mango, or both? Rules don't handle nuances well. The second approach was text-only machine learning models. These models improved on rules by generalizing patterns across large sets of labeled data. Instead of relying on rigid string matches like the SQL approach, machine learning models could infer context, like identifying sugar-free even if the exact word sugar-free wasn't present. What is the downside? Well, building and maintaining these models could be resource-heavy. Each attribute requires its own dataset, model training, and a production pipeline. Scaling this across hundreds of attributes becomes expensive, slow, and complex. Both above-mentioned approaches, the SQL one and the text-only machine learning models, they also share a key limitation. They only look at product text. But in retail, critical information often lives in images. Think of the cereal box that displays serving size prominently on the front, or tissue boxes showing 124 sheets in large font. Text-only messages will miss all of those. To overcome these challenges observed, The team built up the system called PARSE, short for Product Attribute Recognition System for E-commerce, PARSE. This is a self-serve multimodal platform powered by large language models. By saying multimodal, we mean it can use both the text and images as inputs. And thanks to the zero-shot and few-shot capabilities of modern large language models, teams can configure new attributes without having to build separate machine learning pipelines from scratch. The system PARSE has three main components that together handle the full attribute extraction workflow. The first component is the platform UI. This gives teams a straightforward way to set up attribute extraction tasks without deep coding knowledge. Users define the attribute name, type, and description. For example, a string attribute for flavor, or a Boolean attribute for organic. They also select the large language model algorithm, configure the prompt template, and specify which product data should be retrieved via SQL. If needed, they can also provide a few examples to help guide the large language model. The second component is the machine learning extraction endpoint. This is the engine that actually performs the extraction. For each product, it builds prompts by merging the product features and attribute definitions into the chosen template. It then sends the prompt to the large language model to get the extracted value. More importantly, the endpoint supports multiple extraction algorithms, which can let the teams to balance cost and accuracy depending on the use case. It also produces a confidence score for each result. Low confidence values can later be flagged for human review. This is a way to ensure better data quality. The third component of the system is called quality screening, and this component ensures reliability. In the development mode, the team evaluates small samples manually, or they can also use large language model as a judge, essentially asking another large language model to grade the outputs of the results. In production environment, they add a human-in-the-loop layer, where low-confidence extractions are sampled and reviewed. This combination keeps the catalog data consistent and trustworthy at scale. After looking through all the three main components, what standout advantage of the system lies in its ability to merge text and image inputs. For instance, if the packaging shows 80 sheets, but the text description doesn't show this, the system can pick that information up from the image. If a product listing says 3 boxes of 124 tissues, the large language model can also accurately reason through the math. 3 times 124 equals 372. And often, this large language model can cross-reference both text and images, using one source to double-check the other. So, how much better does this work in practice with this LLM-based system? In testing environment, the text-only LLMs already outperforms rule-based models in both precision and recall. But when we're looking at multimodal LLMs, recall improved by an additional 10%. This is a meaningful gain in coverage, capturing cases that would have slipped through the text-only models. Now, we've discussed both the business problem and the technical solution. Let's wrap it up. In this episode, we explored how Instacart tackled the challenge of extracting accurate product attributes at scale. We walked through SQL rule-based approach, text-based machine learning models, and finally landed into the multimodal LLM-based platform. By blending text and image data, this approach enables rapid configuration and helps to improve the recall and accuracy of the system. This case study highlights how large language model can help to streamline data pipelines and reducing engineering overheads and deliver better user experience. If you like the content of this episode, please subscribe to the channel. Give me a 5-star review and leave a comment. Your feedback is very appreciated, and I'll see you next week.